Hello, and welcome back to the course. So today we're going to talk about Schwarz's lemma, one of my favorite lemmas, or uh, one of the uh, one of the most important lemmas in one complex variables actually, and this is subsection 3.5.1. All right. So you may already sort of think, well, how come this is, one of the most important lemmas? If we're talking about, well, let's suppose that we have a holomorphic function from a disk to the disk. It seems awfully specific. Anyway, so let's suppose that we have a function from disk to the disk, and let's suppose that it takes 0 to 0, right? It takes the origin to the origin, and it takes the disk to not necessarily onto, just, it goes from the unit disk, and its values are in the unit disk somewhere. Then we have two things. It's really kind of the same thing, but the first thing is that we have that f is bounded by absolute value of z for all z. Now this should be really, really, really weird, right? I mean, how come? This is just saying, right, that the image is d. It just says that f of z in absolute value in modulus is less than 1, right? But now we're actually saying, no, it's not just that. As you're going from 0 towards the boundary, you're going to go really fast. You have to do at most like the linear guy, right? You cannot go really fast and then slow down or something, right? You have to go below the linear guy, below mod of z for a holomorphic function. All right. Now the second part is this really says nothing at 0. Right? If I just look at it like this and I just plug in z equals 0. But if I take really the limit of that, really if I divide by z, we get this guy, right? So it's kind of the limiting version of number 1, right? That's the thing that actually says something at the origin, right? Now, furthermore, so we have these two things. That's one thing, but we have more. There's more to this lemma. If either one of these equalities, either this or this, inequalities is an equality, right? So either if there's just one z naught, not the origin, because it's always true, but if it's just one non-zero z naught, where you have that the modulus of f of z naught is equal to the modulus of z naught, or if the derivative has modulus 1 at the origin, then f is just this linear guy. I mean, it can have a unimodular constant in there in front. E to the I theta is just some fixed constant of modulus 1, right? That can be there. But that's all that f can be. If you get an equality in either one of those, right? At just one point, right? You get an equality at one point only, right? Up here, can't be 0, right? At 0, you have to have equality in the second guy, but at just one point, you have equality everywhere, and it just is just equal to to some unimodular constant times z. Now, it might sound very specialized, right? We're talking about a holomorphic function from disk to disk that takes 0 to 0. But, a disk is a basic neighborhood in the complex plane. So immediately we see, well, I mean, everything could just be translated and rescaled and you can figure out what that would say for. This is good exercise actually. If I have a function from some disk and it's going into some other disk, right? So I have some bound, and it's it takes some point to some other point, and it's I have a bound for how far it goes over there, right? So it's between two different disks. There's a version of this, right? It would be sort of messy to write it down, so it's easier to write down this version of it. But you can write that down, right? And that basically tells you something about how holomorphic functions behave locally, right? So this lemma tells you something about local behavior. Now, we'll see a bit later that every domain, if it doesn't have a hole, except C, not all of C, but every domain that has no holes, we'll make that precise later on, is actually biholomorphic to unit disk, right? So there's a biholomorphism between that domain and D, and so this is really about global behavior as well. That's actually that seems like maybe a little hard thing to use, but there was when I took complex analysis in graduate school, and on one of the exams, I actually managed to solve every one of the problems by using that term, the Riemann mapping term, and Schwarz's lemma. Even if it didn't really, if you didn't really have to use that, it's actually quite a powerful combination. All right. So let's prove this. So we have that f takes 0 to 0. So let's write f in a power series. We write it as power series at 0. So there's just z to the n, and we notice that n starts at 1 because f is 0 at 0. There's no constant term, right? Or the constant term is 0. So we can write it like this in a power series, and the series converges in the disk. Now, because there is no constant term, I can factor out a z, right? So I have z times this bit. It still converges in the unit disk, right? So what we have is there's some function g, which is a holomorphic function on D, right? And we have that f is z times g, right? That's a very useful thing that we'll just keep doing over and over. This kind of idea. All right. So now take any r between 0 and 1, right? That's something less than 1, right? And we're going to try to get, we're going to be taking limit as r goes to 1 from below. Now, let's take any z on the circle, right? Of radius r around 0, right? And we look at the modulus of g, and we notice that for those z, right? Modulus of z is r, right? That's the whole whole definition of what this set is, right? And f, f goes into the circle, right? So therefore, I wanted this. Therefore, we have that g. Therefore, we have that f in modulus is less than 1, and so therefore we have that g in modulus is less than 1 over r, right? Now, maximum modulus principle says that if this inequality for this holomorphic function g was true on the boundary of the circle, it's true inside, right? So therefore we have that g of z in modulus is always less than or equal to 1 over r for every z inside the disk as well, right? Now, Now we can fix z and let r go to 1 from below, right? Fix z, and it's once r is large enough, and so it's close enough to 1, that z is inside those disks, and so we have this estimate, and then we have it for all those r, right? And then we take the limit as r goes to 1 from below, and we get that g is less than or equal to 1 in modulus. Right, and this is true for any z in the disk, right? Well, what does that say? Well, if I have the modulus of f is equal to modulus of z times the modulus of g, well, if the modulus of g is less than or equal to 1, what do I have? Is exactly the thing that I wanted, right? At least part 1 of it, right? I have that f of z in modulus is less than or equal to z, modulus of z. And you can see that it's really, the key point here is the maximum modulus principle, right? And we get part 2 fairly simply. If I look at the derivative, well, what's the derivative at 0? It's this limit of f of z over z, right? And that's just g, right? And g is continuous. G is holomorphic, therefore continuous, right? So if I take the limit as z goes to 0, that's just g at 0, right? And we know we still have this same estimate. G is always less than or equal to 1 in modulus, so g at 0 is in particular less than or equal to 1, right? So we've proved the two points. Now we have to prove that if we had an equality at one point, we have an equality everywhere, and we actually have that f is just this linear guy, right? So suppose that we had that f in modulus is equal to mod z naught at some z naught that's not 0, right? So right, again, at 0 it wouldn't make any difference because f of 0 is 0, right? So let's suppose that we have such a z naught, right? So what does that say? That says that because g is equal to this guy, right? Well, if these guys are equal, that means that g in modulus is equal to 1. G is always less than or equal to 1. Therefore, g attains a maximum on the disk. Therefore, g is constant, right? Again, maximum modulus principle. If g is constant, well, that, what does that mean? That means that f is some constant times z, right? And that constant has to be unimodular, right? Because of this, right? So we're done in this case. What about if the f prime in modulus is equal to f prime at 0 in modulus is equal to 1, right? If this is true, same idea. Again, it would mean that g attains, right? There would be an equality here, right? So therefore g attains its maximum at the origin. Again, it has to be constant, and again, this has to be true, right? Because this would be, right, f prime would then be that e to the I theta, and we're saying it's 1 in modulus. All right, so that's the proof. We have the lemma, right? Now let's consider the statement for z to the n. It, that's probably the one to, the function to think about. I mean, all holomorphic functions are, in the end, we're going to see they sort of look like z to the n. So it's good to consider z to the n and see what this lemma says, right, for this particular function. Even though we don't really need the lemma for this function, we can just deal with it on its own. But let's see what it says for this function, right? And let's suppose that n is bigger than 1. It's not the linear. Right, now z to the n takes d to d. Actually, it's on 2 even, right? And takes 0 to 0. Right? And for non-zero z, we have that the nth power of z in the disk, right? So non-zero z in the disk, right? The nth power is going to be strictly less than modulus of z, right? And basically, you can see that. So that's that's part one. Part two is even easier. I just take the derivative, and I notice that 0 is less than 1. Okay, right. But something that you notice is that if you had an equality in either one of those, if you maybe allowed one possibly, right, modulus of z to the n, if it's equal to modulus of z, right, for some non-zero z, well, that just means that n is 1, right? That's precisely the what the lemma says. Same thing here, right? If f prime and f is just z to the n, if f prime at the origin and modulus is equal to 1, that means that n is 1, right? Yeah. Kind of boring, but it's good to consider it on a simple example, right? Now, so that just says that that's what the lemma says, but notice something. The bound on the derivative does not hold at other points, right? If I look at some other z, right, non-zero, then you will notice that I have this n in there, right? And I can pick a z that's sort of close enough to the boundary. I can make this as large as I want, right? So the derivative is not going to be bounded ever. It's only bounded by 1 at 0, right? But elsewhere, I don't really have a bound. I can make f prime in modulus arbitrarily large, right? So it's there's not going to be any lemma that says that that's that's always bounded, right? But it's bounded at 0. Now it's a little weird if you think about it, right? It says that if I start, I'm in the disk, I started at 0, I had an arbitrary function that goes into the disk, right? I'm not supposed to go further than distance 1 from the origin as I travel, but so the derivative is like my speed, right? So it says that I'm only allowed to start with speed 1. Then I'm allowed to speed up only as I'm approaching the boundary. But I cannot start really fast and then slow down. That doesn't happen for holomorphic functions, right? If you were talking about just a real differentiable function, yeah, you can do whatever. There's no such lemma for real differentiable functions. Right, this is really something about holomorphic functions. All right, now also if I look at the first inequality, the modulus of f, I can make the modulus of f arbitrarily small. Also at any fixed z by picking n large enough, right? So that inequality can also, I can do, I can break that as much as I want, right? It cannot be any bigger than mod z, but yeah, it could be arbitrarily close to 0, right? Even for z to the n, right? And for if it's not z to the n, it could even be 0 at other points. So, all right. So Schwarz's lemma says that all holomorphic functions sort of behave like this stupid example, right? Well, you have to read that in the right way, right? It's not that every holomorphic function is z to the n, right? But it's, the intuition that you get in this setting from z to the n is the right one for all holomorphic functions. All right. Now, as I said, it's a useful exercise to try to rewrite the lemma for these sort of functions, right? It's basically going to be the same thing, just with R and S and P and Q inside those formulas, making them a bit uglier, right? But it's a useful thing to just to know how that works through the lemma. Now, using an LFT, we had an LFT before that took the unit disk to the upper half plane or vice versa, right? And so we can get an upper half plane version as well easily. And that's if I have a function from the upper half plane to the upper half plane, holomorphic, it fixes I, that's like R0, then we get these two inequalities. So another interesting and a little bit more challenging exercise. It's the generalizations. It's a version of this theorem that maybe doesn't completely look like it, but it's still this sort of theorem can actually be generalized in, for example, several complex variables. Sometimes called the Cartan uniqueness theorem, and it goes as follows: suppose U is bounded. F is holomorphic, and takes U to U and fixes a point in U, right? Then you can show first that the derivative at P cannot be bigger than 1 in modulus. So it cannot, it's sort of the same thing as the item number 2 in the Schwarz's lemma, right? But now it really works for any any function as long as you get, it has to fix the point, right? And part 2 is that if this derivative is actually 1, right, then F is just the identity, right? So, which is kind of weird, right? It's actually a very useful theorem in several complex variables, but even in one variable. But you just have to check the derivative. Just to show that the derivative is 1 at one point, right? That's what it should be for an identity. But you just need it at one point, and suddenly it's an identity everywhere, right? Now, a hint on how to do this, because this is a little bit more challenging. You could always just assume that P is 0. It's a function that takes 0 to 0, and you consider the series expansion of the Lth composition of F with itself. So you compose like this, and you try to figure out what the power series is, at least certain terms of the power series. You really look at the smallest non-zero terms, right? The first two smallest non-zero terms is going to be what you need to look at. So for part 1, you look at the linear term of this guy, and you try to figure out what happens as L becomes larger and larger. For part 2, you use Cauchy estimates on the first basically the second non-zero term of this in the expansion, using this, you'll find that it will end up having to be 0, right? So that's going to be the linear term is going to be the only one that's there, the only one that's left. All right, so that's it for today. And next time we're going to look at one of the other uses of Schwarz lemma, one of the sort of the typical uses of Schwarz lemma. We're going to look at automorphisms of the disk. All right, so see you next time.